Hey everyone, today we'll be going over graphs today, particularly focusing on a brief overview for how we built our unweighted graph, and without any further hesitation, let's get started. And now to go over what we have built entirely. So, first off, what we did entirely for our unweighted graph is that we made an unweighted graph printer header file where we included our necessary libraries, defined a class, have a public instance to print the graph that will be called upon when we are printing out the necessary graph as well. In the case of removing, and then a vertex and an edge, and the overall graph as well, indicated down here in our terminal output. And then we had two private functions to render the graph and draw the arrow that we have also called upon to be able to actually print out the direction of the graph. So technically this would be a directed unweighted graph, since we have the combination of directed, which is indicated by the arrows, then we have unweighted because there is no value, or there are no values on the edges as well. So you can also get rid of the arrows at the same time. You would not need this, and you would still get the same output and therefore get an undirected, unweighted graph as well. And then inside of our main file, so what we have done for the following is that after we have included our libraries and then also using namespace std, we have a class called unweighted graph, where we built out our variables, and we have a constructor that we're able to call upon inside of our main function as well to be able to build out our necessary vertices as well, since it is indicated as a parameter at the top over here. Then we add an edge, as we have indicated, by putting respectively with vertex v and vertex w as well, so that way we're able to output our following graph adjacency list and be able to perform depth first search and breadth first search both iteratively and recursively. Then we removed a vertex as going down and further. Right over here, we have 3 in this case that we have already removed. And then we also removed an edge at the same time, going down here, since we removed an edge by doing the same type of principle that we did with adding an edge, except for we called upon remove within the vector STL library. And also, when we remove a vertex, we have neighbors as a bit of a function as well, where once we remove the following neighbors of a vertex, we're able to use our adjacency file to be able to clear inside of the adjacency list. So that way we're able to isolate and fully separate that vertex at the same time. Notice the similarities of what we did before, except for we called upon different functions from the vector library. Then, when we perform depth first search iteratively, what we did is that we just had one function that we would use, and we would use a stack, since stacks operate based on LIFO, last in first out, and we push each vertex inside, and then while indicating that, saying, hey, while the stack is not empty, we have to check the top of the stack, and then we're going to pop it. And when we are checking the vertex that is inside of the stack, if it has not been visited, we're going to indicate and output that this vertex will be listed out accordingly, and then we're going to reiterate. Make sure as well, but they're all spelled correctly. So make sure at the same time that it is also that you are also spelling everything correctly as well. So that way that makes sense over here. And then you'll have a for auto loop to indicate exactly throughout the rest of the adjacency list, saying, hey, at the beginning, but since we are operating with stacks, stacks operate based on the top, and then at the end, because that means go for the bottom of the stack, like a stack of plates, just visualizing like that. Then we're going to push our index value, saying, hey, if this following index value has not been visited, we're going to push it inside of our stack to therefore check in particular of when the following has been visited. And then we're just going to output the following at the same time. So that's the iterative. And then recursion operates based on two principles of really just using two functions in general, and indicating and re-indicating that, hey, if a vertex is visited, then we're going to output the following. And then with that, we're also going to use a for auto loop to be able to check through our adjacency list to see if it has been visited or not been visited. And if it has not been visited, then we're going to put the indicator at the top, so that way we can declare saying, hey, we visited it again, and we're going to output the vertex as well. and we used a start function to be able to call upon inside of our main class overall. Since principles of recursion typically use a helper function and a function inside of a function, since if we were to go up, we notice that our actual function that we call uses the helper function that we made over here. And yeah, that would output def for search accordingly in the same instances and values that we have. Now, the differences between breadth for search and depth for search is that breadth for search operates based on FIFO, first in, first out, like a grocery store queue for the most part. And what we use is that we use a vector to indicate that what has been visited and what has not been visited, since we have a vertex right here that we use from the top and right here. Then going all the way down, indicate what has not been visited. Then we initialize our queue. Then we're going to say, hey, the vertex that we have implemented inside of our vector is going to be set to true now, even though we have initialized it false. It's just the first vertex that we have already implemented from our parameter. It's going to say, hey, we first visited. Then we're going to push that inside of our queue. And while the queue is not empty, we're going to check the front of the queue, since queues operate based on first in, first out. And we're going to output each vertex accordingly and keep popping it, saying, hey, this has already been visited. Then we're going to keep scanning through our adjacency list to indicate at the beginning, and then we're going to have an index over here at the start of the beginning, and then an index at and while the index is not approached the end, we're going to increment, indicating that if the index has not been visited, we're going to say, hey, this is true, and then we're going to push our following index value, hence star I, inside of the queue to therefore see, hey, what has been visited and what has not been visited. And we're just going to keep doing that until it actually reaches at the very end. So this is just iterative. It's just one function, one go. And yeah, there are no helper functions as well. People like iterative, people like recursion. It really depends what you're working with. And then recursion operates the same thing that we did for depth for search, except for differences is that we're operating based out of a queue, have the following parameters, and then also our Boolean vector as well, indicating what has been visited, what has not been visited. And if the queue is empty, we say return. Then we check the front of the queue, and then we pop it, printing out each vertex. And then we use a for auto loop to scan through our adjacency list at the beginning. And if the index is not approached at the end of the queue, which means the very front, at the very back, because queues operate first in, first out, then we're going to keep implementing our index. And then if the value if the following value from our adjacency list is therefore not been visited, we're going to say that now it has been visited, and we're going to push the value inside of our queue, and we're going to use this function to loop around and keep implementing accordingly, indicating what has been visited, what has not been visited, already set in place. So we use the vector to sort of keep track of everything, saying what has been visited, what has not been visited, and use the queue to be able to actually output everything that has been visited. So it's a type of data structure that we use to be able to actually output our following values, and breadth for search is a type of algorithm that we use to be able to actually move forward and be able to keep track of our following values. Then we have a recursion, breadth for search recursion start. It calls upon the function breadth for search recursive. Hold on, there we go. Calls upon our function that we have over here after we have initialized our Boolean vector and our queue as well, since it is a parameter of queue and Boolean vector. Then we're going to push our following vertex that we have, since we have vertex as a parameter over here inside of our queue, saying, hey, what is this value, has been visited, not been visited. Then we use breadth for search recursive to indicate and run through our logic necessary. Since this is our helper function, this is the actual function we call. And people like this because it can be easier to implement compared to iterative, depending on the complexity of our tasks. So you would do that, the following output at the end. And then we have done so already here. Breadth for search, and we notice the difference that we have already made, 0, 1, 5, 2, and 4, since breadth for search goes based on level. Already here, we notice, to be able to start, notice the pattern of 0, 0, 1, 1, 5, 5, then 2, 4, and 3. Look, 0, 1, 5, 2, 4, and 3. I'll do it again. 0, 1, 5, 2, 4, and 3. 0, 1, 5, 2, 4, and 3. So there we go. implement it like that. I'm going to zoom in for the sake of it. And yeah, so this was building out our unweighted graph. We noticed particular principles that we have combined, such as a directed unweighted graph, because we have arrows in this case, and if it was an undirected unweighted graph, it would not have arrows and would not have values on their edges. Really, the principle of unweighted is that, hey, this graph has no values on the following edges, unlike a weighted graph as well. So that's a key indication that we have. And now we have already finished our unweighted graph, let's head over and focus on cyclic graph as well, and then we will see how well it compares with other graphs at the same time. So yes, I also have the links in the description as well from our GitHub repository, so feel free to play around with the code at the same time, but it's also great practice to be able to code along and actually understand the whole principles behind such. So yes. Hey everyone, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions or suggestions, please put them in the comment section. And as always, take care. Cheers. Bye-bye.